Hello everyone, this is this video lecture, second part of section 8.4 of Calculus 2, Math 2520. Okay, so last time in part 1 of section 8.4, we learned the definition of absolute convergence. A series is said to converge absolutely if and only if series of absolute value is convergent, right? When you take absolute values of every term of the underlying sequence, if you add them up still convergent, then the original series is called absolutely convergent. But if your series is convergent, yet absolute value series is not convergent, then we call the original series convergent conditionally. Converges condition. And then at the very end of the part 1 lecture of section 8.4, we saw two examples. One is, this one is absolutely convergent because absolute value series is 1 over n squared by p series test, p equals 2, which is greater than 1, so convergent. But of course, as it is, without taking absolute value, this is definitely convergent because you can use alternating series test. So this absolutely convergent series is convergent series. By itself is convergent series. Not only the absolute value series is convergent, but the original series itself is convergent. On the other hand, alternating harmonic series is not absolutely convergent. It is conditionally convergent. Okay? Okay. I have to check the video. Okay, so alternating harmonic series is conditionally convergent. Well, by definition, condition convergent series is convergent series. Okay? So, that example gives us this observation. As you can see on the bottom of page 4, no, not bottom, in the middle of page 5, but series convergent does not necessarily mean this one is absolutely convergent. This is a counterexample. All right? What about the other way around? What if your series is absolutely convergent? So absolute value series converges. Does it guarantee the original series also convergent? At least one example, seemed to suggest that. But just one example doesn't prove the statement. And this is very important. It turns out to be the case. That is theorem 3. All right? Theorem 3 is that if series is absolutely convergent, then it is convergent. Okay? So absolutely convergent means absolute value series converges, then original series converges. This is very, very useful because all the convergence tests of the series so far we learned are all about positive series. Okay? All the terms of the series are positive. Possibly except for the first finite exceptions, but eventually all positive. The only convergence test we have for non-positive series is alternating series, like this. Okay? But that's very limited. Useful for limited kind of series. So if we can prove this, then when you don't know how to handle not positive series, if you can show that absolute value series convergent using those tests which are applicable for only positive series, like direct convergence test, direct comparison test, linear comparison test, and the ones we're going to learn today called ratio test. All of that will be available for positive, absolute value series. So sometimes it is easier to show absolute convergence rather than easier than trying to show the original series conversion directly. Okay? So now the proof is actually it's easy actually. First of all, we're going to use this comparison test actually. We know that an plus absolute value of an. An is less than or equal to absolute value of an. So an plus absolute value of an is definitely less than 2 times absolute value of an. All right? Now, absolute value of n is always greater than or equal to an. The sum is definitely greater than or equal to 0. So, these two make a positive series, right? So suppose that n is absolutely convergent. That means, i.e., this one is convergence. The definition of being absolutely convergent means that this absolute value series is a convergent. Then constant multiple of convergent series is also convergent, right? Then we use this. The bigger series converges, then the smaller one definitely converges because both of them are non-negative, positive. By comparison test, or sometimes we call it direct comparison test. This one also converges by comparison test. Okay? Now, what are we trying to show? Convergence of an, series of an. Now, an can be written as an plus absolute value of an minus absolute value of an. Subtraction of two convergent series, right? Okay. From the properties of convergent series, we learned that if two series are convergent, then a series of addition of terms will be also convergent, and the value will be also sum of those each sum of the series. Therefore, and this one is making convergent series. This one makes a convergent series. That's why this one converges. Okay, so I'm going to just write it. So that's why this one is convergent series. Can be split, right, over addition or subtraction. Also converges. So we just proved that absolute convergence, which means convergence of absolute value series, convergence of absolute value series guarantees convergence of the original series. So we don't have to say that a series is absolutely convergent and convergent, because absolute convergence of the series guarantees convergence of the original series, right? All right, so let's use this theorem in the following problem. Let's do it here. Example 4. Determine convergence of the following. Now, if you write a few terms, sine of 1 radian, sine of 2 radian of n squared, sine of 3 over n cubed. sine of 4 radian over n to the fourth. Okay. Now, unlike the previous example, example 3, this one is alternating series. So we were able to use alternating series test. This one is not alternating series. Look at this. Sine 1 radian, 2 radian, 3 radians are positive because sine of pi equals 3.14 radian. Sine 0 to pi is positive. From pi to 2 pi is negative. So 3 terms are positive, right, before pi radian. And then sine of 4, 5, 6 are negative. Sine of 7, 8, 9. Mostly 3 positive and 3 negative. But pi is slightly more than 3 radian, 3.14. So at certain points, you could have 4 terms either positive or negative, straight. But mostly 3 positive, 3 negative. So it's not even having a regular pattern. So you cannot use all the convergence tests you learned before because those are for positive series. The only thing can be applied for non-positive series is alternating series, which this is not. So then what do? Well, we try to show absolute convergence. So consider sine of n over n squared absolute values. Well, sine of anything will be less than or equal to 1, right? So you can write it this. This is bounded by this one. And 1 over n squared converges. P-series test, right? P-series test. P-series test with p equals 2. Then this is smaller positive series, definitely, by comparison test. Absolute value series is convergent. So that means this is absolutely convergent. By showing this, we can now say that the original series definitely converges. Okay? So it was easier to show convergence of absolute value series than the convergence of the original series. Okay? This is one application. Now, the last important convergence test is ratio test. Before we cover ratio test, let's go back to the most important, I wouldn't say the most important, the most basic, the first convergence series of the kind was geometric series. So if an equals a times r to n minus 1, geometric sequence, right? This one converges if and only if this ratio, common ratio, absolute ratio is less than 1. Now, your r is r for all n, right? That's geometric series, right? So that means this ratio is less than 1. Okay? Same in, so just note that R means that this ratio. Ratio of the next term to the previous term. When that is constant, we call it geometric series. For geometric series, that ratio, absolute value of that ratio is less than 1, guarantees convergence. All right? Then finally we can talk about ratio test. All right. The heater is on in the room, so let me just turn off the heater and come back. All right. Theorem 4, the ratio test. The ratio test, which says that if this one is less than 1, okay, then, okay, in this case it is constant, right? An plus 1 over an is always constant, but we're talking about, but anything other than geometric series, this is not constant. But somehow the limit of this ratio exists as a finite number, and that number is less than 1, then this series converges absolutely. Therefore, definitely original series converges. We just learned the theorem. B. Now, if this ratio sequence exists greater than 1, or does not exist at all, like going to infinity, okay? Either it approaches a number greater than 1, or this one approaches, getting larger and larger without bounds, then definitely this one diverges. C, if the limit of this sequence is exactly 1, then the test is inconclusive. Which means that if this one happens, your series could still be convergent or could be divergent. It can be anything. All right? So that's what we call it inconclusive. Okay? Obviously, rigorous proof is not possible here. You don't even know you don't even know the rigorous definition of limit of a sequence using epsilon method, epsilon n method. But I want to give you some intuitive idea behind this. Okay. Now, think about this. What does it mean by this? The ratio sequence has a limit L, which means that this one is almost L for all sufficiently large n, right? For all sufficiently large n. Now, that means what? Hey, this means that it is almost constant L. That means absolute value sequence is almost geometric. Almost geometric. Geometric sequence with common ratio. It's not exactly geometric, so I'm not going to say that exactly common ratio, but almost a common ratio. L, right? See? Geometric sequence was the case when this one is constant. When you have a limit L, then as n goes to infinity, for sufficiently large n's, this is almost constant value L, right? Almost L. It's almost a geometric series with ratio L. So if the ratio is less than 1, then it is, perceivable. Understandable that this is convergent. Also, if that common ratio of almost geometric series is greater than 1, then obviously it is divergent. Now, when it is exactly 1, then it is hard to tell because it is almost 1, so it could be slightly, less than one side or greater than one side approaching, it depends case by case. All right? So, geometric series, when you have a ratio sequence as a limit, that means that for sufficient large n's, they behave just like geometric series, almost geometric series. All right? So it is the ratio test is designed to capture this geometric feature, almost the geometric feature of the series. You know, geometric feature means that your term is exponential function of n, almost exponential function. So it is designed to capture the exponential behavior of n. Okay, almost. Okay. All right. And let's take a look at some examples. So, first one, example 5. Check the absolute convergence. Okay? Check absolute convergence of this. So let's do this one first. A. Okay. Okay. This is our AN, isn't it? Let's use ratio test. So ratio test. AN plus 1 over AN absolute value. AN. We're taking absolute value, so we don't need this. But just in case, let's write it. Big over AN plus 1. Because we're taking absolute values, we don't need minus 1. This is absolute values 1. So you have n plus 1 squared over 2 to the n plus 1 reciprocal 2 to the n over n squared. So then what do you get? This cancel. 1/2 and n plus 1 squared. Okay. So if you take the limit as n goes to infinity, that is limit as n goes to infinity, 1/2 times, what is it? When you have a polynomial, as n goes to infinity, the lower power terms is negligible. This is 1 plus 2 over n plus 1 over n squared. The other two terms going to 0, this one going to 1. This one going to 1. So 1/2. So limit of ratio sequence is 1/2. Less than 1. So it is absolutely convergent according to the ratio test. Now, I told you that limit of ratio sequence is the common ratio of almost geometric series. Look at this. If you had a 1 over n squared, 1 over 2 to the n, that would be exactly absolute. We are taking absolute value. 1 over n, 2 to the n will be geometric series. Now, even though your n squared is also growing fast, yet, according to ratio test, this will behave just like a geometric series with common ratio 1/2. Just like without it. Right? So, compared to 2 to the n, 1/2 2 to the n squared is negligible. That's what it says. Because exponential function is way more dominant than power function. N squared and even n to 100. Okay? It doesn't matter. Okay. Likewise, even if you have, okay, let's say 100 power. Let's say you have 100 power here. The conclusion will be the same. If you have, say, 100 power, really fast growing. Yet, 100, 100, 100, 100. Then you can write this one as, what is it? This is 1 plus 1 over n. See, n plus 1 over n, whatever power it is, 1 plus 1 over n to the p power, right? 100, still going to 1, because inside 1 going to 1, 1 to the 100 going to 1, so 1 half. Still behave essentially just like geometric series with common ratio 1. See? So exponential feature is way more dominant than power function. So your ratio test is designed to capture that, right? It ignores n to the 100. Okay? It is just like a net for, a fish net for tuna doesn't care about anchovies. Anchovies go through the net freely. N to the 100 will not be detected in the ratio test because your ratio test only focuses on exponential function or geometric feature or even bigger, which you will see here. On the other hand, even if you have a n squared less n to the third bottom, that would have been same result, same thing. n plus 1 to the third, and n to the third, 2 to the nth. So n plus 1 to the third, 2 to the n to the third. You have 1 over n plus 1 to the third. So still, this one going to 1. So it's going to be the same thing. All right? So either you have power function in the numerator or denominator, anyway, it will be ignored in ratio test. B is B. Okay, that almighty exponential terms on the numerator, but you have a factorial function in the denominator. Then what happens? So again, this is your an. So an plus 1 over an plus 1. So we are taking positive, absolute values. So we don't need minus. 2 to the n plus 1 over n plus 1 factorial divided by an means reciprocal. See? I took the absolute value here. What do you get? You have 2. And then, you know what? N plus 1 factor is 1 times 2 plus 3 times all the way to n plus 1. So this is n factorial. N times n plus 1, right? So all cancel, still n plus 1 is remaining. See? That's why n plus 1 factorial over n factorial is n plus 1. See? After cancellation. 2 over n plus 1 is the ratio sequence. Therefore, limit n goes to infinity. What is it? 2 over n plus 1. 0. So that means it's less than 1 according to ratio test. Anything less than 1, absolute convergence, right? Obviously, L cannot be negative because it's absolute values sequence. So exactly 0, less than 1 means this is absolutely convergent. Okay? So that means factorial grows so fast when you, even if you have a basically 2 to the nth in the numerator, when you have in the presence of n factor in the denominator, make it just like a, what is it? Almost 0. That means next term is, right? It's just like a constant zero series, almost nothing. So eventually, when you have an n factorial, as n goes to infinity, it behaves just like a constant series. Zero constant series. Almost nothing, right? Despite the exponential growth in the numerator. Because n factorial grows so much faster than 2 to the n. It behaves just like adding zeros forever, right? Almost. Okay? So that means n factorial is way above the level of exponential function. And you can see this. Why? All n factors, right? What about n factorial? No, it's not n, sorry. 1, 2, 3, 4. Look at this. 2 to the n is keep multiplying by 2, only 2. Here, multiplying by growing number. So you can imagine how much larger this one can be than 2 to the n, right? So it is understandable why this behaves the way it is. Absolutely conversion. The behavior is almost like down to zero very quickly. So the comment is that if you have n factorial above, then what happens? If you have this, then in that case, you just take reciprocal, right? It'll be n plus 1 over 2. The limit is infinity, right? So it'll be divergent. Okay? So if you have an n factor in the numerator, an exponential function of n in the denominator, going to 0. Now, even if you have 100 to the n power, still you have 100 over n plus 1, going to 0. Or n plus 1 over 100, going to infinity. It doesn't matter how large the base of the exponential function is. Compared to n factorial, they are negligible. Okay? So, it turns out that your n factorial beats the almighty exponential function. It turns out the exponential function is not that mighty, powerful, compared to n factorial. That is n factorial. Factorial function is the biggest in town. Well, let's think about this. All right, n factorial is n to the nth power. This is not power function. It's not n to the fixed power. It's a power function. Or fixed base to the growing variable. This is power function. This is exponential function. Now, our function here is both base increases like power function, but also exponential. Exponent also increases, just like it has both increasing. So we can expect that this one grows very fast. Compared to n factorial, how fast? So ratio test. Let's do ratio test. Then n plus 1 to the n plus 1 power over n plus 1 factorial. And then reciprocal of an. This is your an. Okay? Then what do you get? First of all, this one cancels. All right. And then, what is it? N plus 1. So you have this one over n plus 1. 1 over n to the nth. So one power cancels with this. So you have n plus 1 over. Okay? So if you take the limit of this, what do you get? This is 1 plus 1 over n to the nth power. Does it look familiar to you? 1 plus 1 over n to the nth power as n goes to infinity, the limit? You've seen this one before, even in pre-calculus. As x going to infinity, 1 plus 1 over x to the x power is one of the definition of natural base e. Okay? So, through n, same thing. Approaches the same value, which is greater than 2.718 something. Definitely greater than. So, it is divergent. Wow. N to the nth beat out n factorial. Even though n factorial trying to pull it down, n to the nth power is overcome. It's overcoming. Going to infinity. Actually going divergent. Alright? In fact, this ratio test says that in the end, this one behaves just like some constant times e to the n. Almost geometric series with common ratio e. So something times e to the n. That's the way this one behaves. Eventually. Alright? Very interesting, isn't it? Now, if you compare this one here, now you can understand why n to the nth is actually larger than n factorial. Significantly. N factorial is, right? N factors. What is n to the n? This one grows. The factors are growing. Here, factors already reached the highest value of n. Certainly, this is way large, right? How large? The ratio will be almost like e. Okay, that much large. Okay. All right. So, in the end, your ratio test is designed to capture exponential behavior or geometric behavior or larger. This one can detect geometric feature or exponential function of n feature. N factorial will be effect or even n to the n power. So I would say n factorial is like n factorial n to the n is like whale. Okay, fishnet for tuner definitely can feel a whale, right? Either crashing, exploding. All right. All right. Now there's some remark. The ratio test is indeterminate when you have exactly 1. Okay? Now think about this. Let's think about this. So if you have, for example, the remark is about this indeterminate case. Okay, we know that this is absolutely convergent. Absolute value series is 1 over n squared. Converges easily. P equals 2. For that, let's do this. 1 over n plus 1 squared. Well, we don't need minus. Hey, this is n over n plus 1 squared approaches 1. Ratio test just tells you that I don't know. But we know that this is definitely convergent. So ratio test is inconclusive. Because when you have a power function, n squared, either numerator or denominator, ratio test cannot detect anything. It looks like a constant. First term is keep repeating. Ratio, common ratio 1 means that you have a, right? So in the end, it feels like, hey, you have a just constant series. Right? I don't know. What if you have n squared instead? Okay? This is divergent, right? This is divergent. Again, this one, 1 over n plus 1 over 1 over n, so n over n plus 1. Again, the limit is 1. The conclusion ratio test means, I don't know, it's inconclusive. What about this? It's definitely divergent. Even the limit of the sequence going to infinity, there's no way this is divergent. What does ratio test say? N plus 1 to the 10th, n plus 1 over n to the 10th, still converges 1. As I said, ratio test doesn't recognize any power function. It is a fishnet for big fish, net for big fish, not small one. Okay? So it's not useful for many series. The ratio test is very useful when your series has a geometric feature or exponential function feature of n. And that is very, very important case because second half of the chapter 8 is about power series. And by definition, power series will have exponential function feature, geometric feature in it. That's why ratio test plays a crucial role in the second part of chapter 8. All right? So that's the end of section 8.4. This lecture is for the second half of the week of March 30th. So you can consider this lecture be given on Thursday, April 2nd. So you have to finish your work of section 8.4 this week, all right? And try all the homework problems. Okay, so you can ask questions on Thursday, regular Zoom office hour, which is 9 to 10 every Monday and Thursday, either this Thursday, April 2nd, or the next Monday. That would be what? 4 days, it's April 6th, I guess. Okay, so you can ask questions, or you can ask any other questions. All right, so I'll be waiting in the Zoom meeting. Okay. 9 to 10 on every Monday and Thursday. All right? Okay. Well, then see you next time.